Okay, so vectors should not be brand new to you, regardless of what science you're in or what grade level you're in, because they are first introduced to you in geometry, very minorly, but when you're doing translations, they're introduced to you in geometry. Then for those of you in physics, vectors is something that you talk about in physics, right? So our definition of a vector is a quantity that has both magnitude, which is size, and in this case, length, and direction. Okay, magnitude and direction. So a vector looks like an arrow. It looks like a ray, and it can be represented geometrically using a directed line segment, which is a fancy way to say it looks like an arrow, right? We have this P and Q. P is where we start from. It is the initial point, or tail. And then Q over here is the terminal point because that's where it ends, or the tip. Okay, so we have P, we have Q. We start at P, we go to Q. The way that we denote vectors when we name them, it's like a ray. It's with an arrow. So that vector PQ that we have over there, now something disappeared here again because that's what always happens to me. There should be a capital P, capital Q right there, but you would put the arrow over it. It could not be QP, it has to be PQ. And it doesn't matter which direction the vector is pointing. When you notate it, it's always pointing to the right. And then this lower, or just a lowercase p, because that's what's right there, but it would also have an arrow over it, or a boldface lowercase letter with no arrow over it. So you'll see it this way in print, but most of the time when you're writing, we don't use that because it's kind of hard to tell that it's in bold, so you put the arrow over it, just kind of the proper way to do that. Okay, we all good so far? Alrighty, so then a zero vector is just a vector with magnitude, oh, hope if I spelled that right, magnitude 0. Okay. So let's talk about a couple different types of vectors. So I can have parallel vectors. Just think about like when you have parallel lines, right? These have the same or opposite direction, but not necessarily the same magnitude. So I could have a vector that looks like this and like this. We'll call them A and B. So these are not going in the same direction, but they could, and they're clearly not the same magnitude. So I can say vector A is parallel to vector B. Equivalent vectors have the same magnitude and direction. So these would look like this. We're not going to measure, but just do your best to make them look right. This is M, this is N. So we can say vector M is equal to vector N. Then opposite vectors, it's not just about going in opposite directions because these are going in opposite directions. These have to have the same magnitude but opposite directions. And to write the opposite of a vector, so if I have vector A, it's written as negative A, that's what flips it around. So if I had something like this, where this is U and this is V, so they have the same magnitude, they're the same length, but they're going in opposite directions, then I can say U is equal to, vector U is equal to the opposite of vector V, and vice versa. Okay. Any questions at all? All right, so let's identify some of these. It says use the graph below to classify each pair of vectors. So let's find A. Here's A and E. E is over here. This kind of looks like an E too, but that's a C. It's because of where the line is there. All right, so these are clearly not going in the same direction. Do they have the same magnitude? Yes, so if they have the same magnitude and opposite directions, that makes them opposite vectors. Then I and F. So here's I, here's F. Looks like they're going in the same direction. If I want to see if they're the same magnitude, I'm going to go to the right 2 and up 1, 2, 3, 4, 5, 6. So here I'd go to the right 2 and up 1, 2, 3, 4, 5, 6. So they have the same direction and the same magnitude, which makes them what? Equivalent. It's like a $5 word. Okay, so then let's find D and E. So here's D, and here's E again. Clearly not the same size, right? But are they going in the same direction? Yes, and that makes them what? Parallel. Can we put this up here? Oh, you're fine. Okay, I just didn't want to knock your phone off. All right, so then let's look at B and G. Here's B. Here's G. Are they going in the same direction? Nope. Are they going in opposite directions? Nope. They're going in different directions, but not opposite directions, right? And in order to be any of those three, they have to be the same or opposite, and it's none of those, so it's just none. Then C and H. Here is C, here is H. Opposite directions, do they have the same magnitude? Yes, they do. That makes them opposite vectors. Any questions about the super basics, basics of our vectors? We all good? All right, let's move on to the next part then. We're going to talk about the different ways to write our vectors, the different positions they could be in, and so forth. So standard position is when the initial point which is the tail, is at the origin. Now, even though we're going to be thinking in terms of x and y, we are not talking about plotting points. But this vector here, it does have its initial point or its tail at the origin. So here is vector v, right? It is considered to be in standard position. But a vector can be anywhere on the graph. Like I could take this and slide it around. I can't turn it because I can't change the angle, so I can't rotate it, and I can't stretch it or dilate it because I can't change the length, but I could shift it around, could translate it around, and even reflect it. So it says if vector v is in standard position with a terminal point AB, then the component form of vector v, so vector v, when you write a vector in component form, you use pointy brackets. That's how you know you're not plotting a point. It's denoting a vector. And if I needed to get here, just like we counted on the other one, I'd have to go to the right, whatever A is, and up, whatever B is. Make sense? So that tells me how I draw my vector. I go to the right, whatever, right or left, in this case it's the right, and B was my up or down, so it's just A comma B. Where A is your left and right, B is your up and down. It's just like having X and Y. Okay? And then we have the magnitude and direction angle can be given by this. All right, so here's what I know. Well, first of all, magnitude, it looks like the absolute value, but it's doubled on either side. okay? So that's the length of this vector right here. It's the actual length of it. I know what this length is, it's A. I know what this length is, it's B. So to find this, that's Pythagorean theorem. That is A squared plus B squared equals the magnitude of V squared. Make sense? You've known Pythagorean theorem like forever. So when I just want the magnitude, it is the square root of A squared plus B squared. This angle right here, if I know A and B, that's the opposite and the adjacent. So I know that the tangent of theta equals the opposite, which is B, over the adjacent, which is A. That means that theta is the tangent inverse of B over A. Does that stuff look familiar? Does it look a lot like what we just did with polar? Okay, so polar actually comes from a unit called polar and parametric. And we're not completely skipping parametrics, but I wanted to try something different. We went from polar to vector, then we're going to go back to parametric, and I'm hoping it'll make parametric make a little bit more sense. I think it will also help you connect the polar and the vectors a little bit better. Because this is, although we had x and y instead of a and b, that's exactly what we did to get our r theta, right? It's the exact same thing, exact same idea, right? So now we are going to find the magnitude and direction for each angle. Unless there's questions. Are there any questions? Oh, stupid tablets. Okay. Hang on just a second. I have... Here. Just get a pencil and give up. Yeah. All right. Magnitude and direction. So I want the magnitude of vector r. That's just going to be the square root of a squared plus b squared. 7 squared plus 24 squared. That's equal to the square root of 49 plus 576. That's equal to the square root of 625. What's the square root of 625? 25. You should be able to get through that quickly because you should know your perfect squares to 25. You also, and I should have said this at the beginning and I apologize, you need a calculator handy. So the one that I'm going to be using is the Desmos one. It's desmos.com/scientific, but I don't care if you use Delta Math, Desmos, you have your own separate calculator. Whatever it is you normally use for calculations, have it handy. Okay. All right. So then I need to find the direction angle. So that's theta. Theta is equal to the tangent inverse of b over a. So that's 24 over 7. And when we're talking about vectors, we're usually using degrees instead of radians. So we're going to be in degrees here. So on your device, whatever it is you're using, make sure you're in degree form. So if you're on the Desmos calculator, then that would be radians, that would be degrees. Hopefully you know how to switch between the two on whatever it is you're using. So I'm going to do the tangent inverse of, what was it, 24 over 7. And that gives me 73.740. 73.740 degrees. Okay. Oh. What questions do you have? Pretty much the exact same thing we were doing with polar, right? They're very much connected. I mean, the only difference is we're doing it in degrees instead of radians, and we're going to use values that you're not expected to know from the unit circle. I mean, if they're unit circle values, then you're expected to have exact form, but that's not the case here. Okay, so let's look at, actually, you try number 2. You find the magnitude and the direction angle on number 2. Okay, so do you agree with me so far on number 2? So what if I told you we haven't done anything wrong, but 18 degrees is not the right answer? If you recall, but again, we haven't done anything wrong. We're just not finished. When we were solving trig equations with a calculator, and remember that when you take the inverse of tangent, when you take the tangent inverse, you are only getting first and fourth quadrant angles. That's it. And in your fourth quadrant, you're getting negative ones every time. Like, that is how you take the inverse. So we have to pay attention to which quadrant we're in. We actually should have done that on number 1 also. I just skipped saying all that since it didn't matter. Wanted to talk about it on one that mattered. So on number 1, if I think about where this vector goes, okay, as far as, it could be floating around anywhere, but if I'm going to go the right 7 and up 24, then I'm pointing towards the first quadrant, which makes this a quadrant 1 angle, and that's what I got, and so that's why I was fine, right? When we were taking the inverses, and then we had to figure out our quadrants, remember we talked about the reference angle. Your reference angle is alpha. So here, this would be pi minus alpha, this would be pi plus alpha, and this would be 2 pi minus alpha. Remember that? I mean, it was right before spring break, but we did it. So we're talking in terms of degrees here, which means instead of pi, this would be 180 minus alpha, 180 plus alpha, and 360 minus alpha. Now, if you're going to do this, then alpha is the reference angle. It's always in the first quadrant. So whatever you put into the calculator, like in this case, we put in a positive 1/3. But let's say it was supposed to be negative. If I'm going to use that thought process over there, then I have to always put in positive numbers so I make sure I always get a first quadrant angle. But I'm going to show you how you can reason through it regardless of what you put in the calculator, because I think that it makes a little bit more sense. If you have to, I think you think better around the unit circle in radians. But I think if I gave you an angle in degrees, you would be more comfortable with what quadrant it's in than if I gave you a radian angle in decimals. Does that make sense? So I think that, it just depends on which one you're using, which way you want to think about it. And I don't care how you do it. I want you to do it the way it makes the most sense to you. All right? So once I get this, right, what I should have thought about from the beginning was, all right, if this is -3, -1, I'm pointing towards quadrant 3. It gave me a first quadrant angle. I want to be in the third quadrant. So to get from the first to the third quadrant, I add 180 degrees. So if I just add 180 to that, which is basically what's happening here, then that would give me that my actual theta answer is 198.435 degrees. What questions do you have? Do we understand why it's 198 and why it's not 18? Okay. You have to think. You can't just let the calculator spit numbers out at you and you write them down. You have to make sense of where things are and what it is. I don't do this just for your benefit. I would totally do that for myself as well, so I can actually think about which quadrant I'm supposed to be in. All right? So let's do number 3 together. I want to find the magnitude first. It's going to be the square root of 8 squared plus -12 squared. It's the square root of 64 plus 144. So that gives me the square root of 208. Should I leave it like that? No, I should try and simplify it, right? So when you simplify your square root, which I'll tell you, in Delta Math, you don't have to, because when it comes down to it in calculus on the AP test, you don't have to. But all the way through pre-cal and even sometimes in calculus, we still make you do it because you still need to know how to do it, and sometimes it's to your benefit to do it. So I'm not going to take the time to do it because you should know how to do it anyway, but you'd end up with, actually, let me write it this way. You'd end up with 4 times the square root of 13. Oh, come on, board. So we can say that the magnitude of V equals 4 square root of 13. Okay, so then let's do theta. Theta is the tangent inverse of -12 over 8. So when we were solving them on the calculator for when we're just solving trig equations, I said even though it's negative 12 over 8, we would put positive 12 over 8 in the calculator. And that's fine. And if you're doing that, you get alpha, and then you just figure out where you need to be. But if I put in the negative, like there's nothing wrong with it. It's just going to give me a fourth quadrant angle. Let's see, it gives me negative 56 something. I don't remember exactly what it was. I guess we should do it. We could do it. Let's just do it. It's negative 56 something. So I'm going to do tangent inverse. Oh, wrong one. Tangent inverse of, dang it. Okay, thank you. Thank you for not letting here. I'm just going to clear it all off. All right, so let me hit the right thing. Tangent inverse, now I can do it correctly, negative 12 divided by 8. Okay, so that gives me negative 56.310. 0.310. But I don't want a negative angle. Given this right here, which quadrant is my angle supposed to be in? 4, okay? It should be in quadrant 4. This actually is in quadrant 4, right? It's in quadrant 4, but it's the negative version. I want the positive version. So all I have to do is add 360 to that. So in my calculator, I can do, after I hit enter, I can do answer plus 360. And notice that my reference angle would be a positive 56. So this is really the same thing as 360 minus the reference angle. It's the exact same thing. Just depends on how you want to think about it. And we get 303. So theta equals 303.690. Okay. What questions do we have? We all good? Uh-huh. Okay, hang on 1 second. Okay, ask me again. Okay.
You get the answer for the tangent, like how do you know where it's supposed to go in the quadrants?
So when I get this number, how am I supposed to know where I'm supposed to be?
Yeah.
Okay, because this vector, whatever, it's 8, negative 12. So I'm going to go, if I start here, I go to the right 8 and I go down 12. So I know it's pointing like this. And so I don't know where in the rectangular coordinate plane it is, but I don't care because what I need is the direction angle. So I know if it's pointing this direction, it's a fourth quadrant angle. Does that answer your question? Yes?
Yes, thank you.
Okay, you're welcome. Anything else? That's a very good question. Okay, good deal. So you can kind of think, like, I don't want to talk about it like you're plotting a point because this is totally not plotting a point, but if you did think about where that point is, like if it's in standard position, that would be a fourth quadrant point. So it's kind of the same thing, just make sure you know you're not plotting a point and you'll be good, okay? All right, so did I tell you to do number 4? Y'all working on number 4? I don't know if I already said that. Y'all work on number 4. Any other questions, though, while y'all are working on that? Okay. Mm-hmm. Do you have to put the what? I'm sorry? Yes, because this means vector v. This means the magnitude of vector v. They're two completely different things. So I want to make sure that we still get this angle thing. So the angle that it gave me, this I know is a fourth quadrant angle. I'm down here. This, my vector would be pointing towards the second quadrant, because if I go to the left and then up, this is actually going to be a second quadrant angle that I need. So if I'm in this quadrant and I need this quadrant, I can just add 180 to it. So if I add 180 to that, it's going to give me 150 something, right, just off the top of my head, which would put me in the second quadrant, which is what I want. So if I just add 180 to that, I get 151.390. Okay. What questions do we have? Anything? All good? Awesome. Okie dokie. So that's all when they're in that. This magnitude works no matter what, but when they're in standard position, you can kind of think of where it is on the coordinate plane. But if you have, you can take any vector that's anywhere in the coordinate plane and write it in component form. So let's say instead of being in standard position, it's over here. My initial point is x1, y1. My terminal point is x2, y2. But I need it in component form with my pointy brackets. Okay, so then that's very easy to do. That vector v would be, now you got to keep this straight. This is my initial point, this is my terminal point. So I have to start with the end, which is x2, y2. So this will be x2 minus x1, and then y2 minus y1. And that's how we get it in standard or in component form. So this says give the component form for each vector. So this is vector CD. This is my initial point. This is my terminal point. I know that from this because that's the way it's written. So that means I'm going to do 6 minus 3 and 3 minus 5. So vector CD is 3, negative 2. Easy enough? What questions do we have? All right, y'all do number 6. Oh, this says RS. I don't know why this is a B. This should be S. It's not a trick question, I promise. Why are you looking at me weird? Did I subtract wrong? No, I didn't. Ask me a question. Clearly, I said something that confused you. You good? Oh, you're good? Okay. Just looked up there like, oh, okay. I couldn't tell if that was a squinty I can't see or a squinty what the heck did she just do? So that's why I checked. I was like, oh no, did I subtract wrong? All right. We all good? All right, so then it says, give the component form, the magnitude, and direction for each vector. All right, so we have vector AB, and they give us, this is the ordered pair for A, this is the ordered pair for B. So my component form, AB, is, I'm going to take negative 4 minus 9, that gives me a negative 13. And then negative 1 minus a negative 3 is going to give me a positive 2. So that's my component form. Yes?
Can we go back to number 6?
Yes, we can.
Whenever you subtracted 5 and negative 2, why did it say negative?
Because you have to do negative 2 minus 5.
Oh,
It has to be the end minus the beginning. Does that make sense?
okay.
Yes? Okay. And that's why the way this is written is important, because it's got to be the S minus the R. So we have to do this one first. All right, good question. Anything else? All right, so then once I have this, I can do the magnitude. So the magnitude of vector AB, that's the square root of, and then I'm going to use that, negative 13 squared plus 2 squared. What's 13 squared? Somebody, anybody? 169, yes, that's one we should know, right? Plus 4 gives me the square root of 173, and we can't simplify that. So then the magnitude of AB is the square root of 173. So to go back to David's question, which is, do we have to put these little lines here? And yes, because if I don't have it, that's naming the vector. If I do have it, it's telling me the magnitude. So that it means different things. All right, so then the direction angle. Theta equals the tangent inverse of 2 over negative 13. So you find the angle and make sure you know which quadrant it's in. So that negative, it gave me a fourth quadrant. I want it in the second quadrant. So I just add 180 to what I got. And I get 171.254 degrees. What questions do we have? Anything? We're all good? Okay, awesome. All right, so let's look at number 8. So on number 8, first of all, the vector itself is in quadrants 1 and 2, but that's not how I decide where I want my angle to be. My angle has to do with the fact that I need to know which way it's turned. So when I'm looking at the angle, doesn't matter where it starts, this angle is still going to be a fourth quadrant angle. So it's going to be a quadrant 4 angle that I need in the end. For component form, I could find the two ordered pairs here and do my subtraction, but I can also just count. Yes?
How is that quadrant 4?
Because if I'm just talking about the direction that this is pointing, it has nothing to do with this x and y. It has to do with the unit circle type thing, where if I start here at 0 and I rotate around, that angle right there is a fourth quadrant angle. Does that help? Yeah? Okay. So that's why I wanted to give you one on the coordinate plane. It doesn't have anything to do with where this is sitting, because this could be sitting anywhere. Doesn't matter where. But so it's a quadrant 4 angle that I want. My component form for vector C, I can just count. So if I start here, I would have to go to the right 1, 2, 3, 4, 5. So that's a positive 5. And then I'd have to go down 1, 2, 3. So then that's a negative 3 for that B value. Magnitude, I'm going to have to find the same way I've been finding magnitude. So the magnitude of vector C is the square root 5 squared plus negative 3 squared, square root of 25 plus 9. So the magnitude is the square root of 34. Then you find the angle. Okay, so this is what the calculator gave me. That is a fourth quadrant angle. And I want a fourth quadrant angle, but the thing is, I want this angle. It gave me this angle. So then if I just add 360 to that, I'll get my actual angle, which is 329.036 degrees. Because if I have a negative number right here, that's basically how much I'm subtracting from 360 to get to that. So since it's already negative, I just add 360. It's the same as 360 minus that reference angle. That's why it's good. Like if I have a graph, I'd probably look at it on here. If not, then I'm going to be thinking about, like drawing it like this and thinking about where I'm going. Okay. What questions do we have? We all good? All right. This last part is super quick, super simple. It says vectors are equivalent if and only if they have the same component form. So we know if they're equivalent, they have the same magnitude, the same direction. And so we need to see if they actually have the same component form because I don't want to graph them. So we'll just find that real quick. AB, make sure you're subtracting in the correct order here. AB means B is the end, so I have to start with B. And I'm going to do -7 minus a -3, which is going to be a -4. Then -2 minus 6 is -8. By itself, that tells me nothing because I have to compare it. So I have to find the other one, CD. And that would be -1 minus 3, -4. -9 minus a -1, -8. These two are identical. Therefore, vector AB is equivalent to vector CD. Okay. What questions do we have? All right, you do number 10 and we'll be done. Are they equivalent vectors? No, because this one has a -6, this one has a +6, so then we have to say they are not equal. There's our answer. Okay. What questions do we have? Anything? All right, so your Delta Math assignment should be fairly simple today. Remember that tomorrow it's an asynchronous day. Make sure that you answer the discussion question that's in the folder. Make sure that you watch the video and take the notes, and there's an assignment. It will all be open and ready to go at 7 a.m. Yes, ma'am? You do not need to submit work for this, no. Okay. Any questions at all? All righty.